everybody. So we are at the last two lessons, 2 hours of lesson. And in the first day, we discussed a little bit in details about a geothermal field, the one at Amiata. In the second day, we went and discussed what are the major ways to try to tackle geothermal field problems, and we understood a little bit analog modeling. We discussed also the equations, the analytic modeling with the equations that govern the fluid dynamics of porous media flow in geothermal systems. And today, we are looking at mainly at some models. Well, we went first to look at how the most simple geothermal power plant works. We overview very briefly some of the new technologies that are for the future of geothermal energy. And then we started to do some analysis of some of the models that that describe geothermal systems. And one of these, the first I've shown you, is a model that attempts to use CO2 in place of water to run geothermal systems. We have seen that CO2 is very efficient in driving the heat out of the rocks to the surface. However, it creates some problems that are related to clogging of the fractures that provide the main permeability for the fluids to flow from the hot rocks to the well. Now, this afternoon, I would like you to go through another model, a very simple one. We said that one of the major problems or things that we need to know in geothermal energy is permeability, and that this permeability is mainly fractured permeability, and therefore I like to show a modeling of a fault, of how behaves a fault in a geothermal system with particular relation to CO2. Now, the reason why this modeling was done is that on the one hand, it's extremely important to have faulting and fracturing in our geothermal system to produce permeability, but also we would like to know where these fault or fractures are. So this modeling is trying to show what will happen if you will inject CO2 into a fault, and then very briefly how you can try to image this fault through seismic analysis. Do you see my desktop?
Yes. Yes.
So this is one of the many geothermal fields that are present in the Basin and Range province between Nevada and California in the United States. Most of these geothermal systems, some are related to actual magma erupting to the surface, some are not, but are mainly related to delamination of the earth crust, so that hot heat from the deeper horizontal layers of the middle and lower crust are brought to the surface. Now, in this case, you get a very large set of faults, of normal faults, that delaminate the upper crustal rocks. This is in particular is the rhyolite ridge desert peak geothermal system. There are a very large number of hot springs around and also gas emissions around there. Most of these geothermal systems are exploited with binary plants simply because there is very little water around, so they can cool down only through the air. The rhyolite ridge fault system, as you see, is a set of normal faults that are merging to the west. And I'm going to show what the part that we want to model is the model fault is the one here, is the last fault of a set of 3 faults. Hey, what's happening here? Preview, why is it not? Okay, so this is the square we saw before with the 3 faults. We are going to model this fault here and how it behaves by injecting CO2 through this well out here. So first of all, we have built a very detailed geologic model of this fault from down at depth to the surface. Most of the sequence here, the geologic sequence, are volcanic rocks, and in the lower part, there are low-grade metamorphic rocks. So the first that we have done has been to simplify our field model, making straight faults and sort of inclined but straight rock units. So you have the Mesozoic meta-sediments at the bottom. This is where the geothermal field actually is, with the Oligocene tuff being slightly altered, which is a little bit impermeable and stops the cooling of the geothermal system from the little rainwater that is coming from the top. And we are actually modeling a little bit this fault. So this is the model, how it works. This is sort of a true scale. I have a groundwater water table 30 meters below the surface. I have an inclined fault at about 60 degrees and a set of rocks that are the various rocks that we have seen in the cross section. And as you can see, these rocks are displaced across the fault. But I'm actually modeling also the fault gauge in between the rocks on the side. So the full model is between minus 915 meters for an additional 940 meters. If I expand this model laterally in the x direction, this is what I get. This is actually how you see the model, and I need to expand it, otherwise it will be too difficult to show you how the fault gauge is modeled and how is the damage zone modeled and the intact rocks on the side, the rock matrix. As you see, there is intrusive basement, the Mesozoic sediments, the Oligocene tuff, and the rhyolitic lavas. These are integer and have a little bit of fracturing. And then you have a damage zone, which is about 20 meters wide, with a very fine detail, how do you say, detail grading in the damage zone. The damage zone is where you have a lot of fractures, much more than the intact rock formation. But then you have a fault gauge, which is all this part here, and the fault gauge is really the rock formation are all broken up, so you have even more damage in the rocks than in the damage zone. And then there is a slip plane right at the center here, where you get the highest permeability. So actually, you might imagine that there is a little bit of leakage from the geothermal system through the slip plane in the fault gauge. The slip plane is only a few millimeters across. Again, you have a fault gauge and a matrix on the right-hand side of the fault again. The fault here, it doesn't look like at 60 degrees, but this is just an effect of enhancing the X direction of the system. Now I'm injecting CO2, supercritical CO2 here, and I will show you that the CO2 remains strictly inside the faults and never enter the rocks, even the damage zone. And the reason is that the full system is saturated with water at the beginning. So as you inject CO2, the CO2 is not able to displace the water out of the pores of the rocks and out of the smallest fractures. And so the CO2 remains concentrated in the fault zone. And because of this, then you have a very strong change in impedance of for the seismic wave to go through. So the seismic waves do not like to go through the CO2 saturated fault zone, and that allows you to actually image how the fault zone is done. It's a little bit trying to do an X-ray with a contrast fluid, but instead of doing to your body the X-ray with a contrast fluid, we try to do it into the ground with the contrast fluid being the CO2 and the body being the rock itself. This is the first part of the modeling, and you can see that red means CO2 saturation. So I'm injecting CO2 in the fault zone. I'm injecting the CO2 in the fault gauge. At the bottom here, I'm injecting CO2 into the into the fault gauge. Now, as time passes by, you can see that the fault gauge is fully saturated at the beginning with CO2. Now, as time passes by, you see that there is a CO2 plume in green, which about 0.5 CO2 saturation in the fault gauge. And as you can see, the fault gauge becomes saturated only on the upper part of the fault gauge. relative to water, the CO2 is much more buoyant and therefore tends to flow on the roof of the fold and tend to flow upward following the roof of the fold. The CO2 does not enters the fold matrix. And this is because the surface tension of water is so high that the CO2 cannot penetrate the water-saturated fault gauge, damage zone, and matrix, which is even farther away. Any question?
No.
So as the plume develops, you can still see that the upper part of the fold becomes saturated with CO2 at about 50–60%, but as the plume grows up, because of expansion of the plume and because of transition from supercritical fluid down here to a more closer to a fluid that is not supercritical, then you get a larger expansion and the flow start to approach also the slip plane of the fluid, of the fold. Now, after 4 days of injection, then you have your fold plane that has, in the lower part, has reached about 70% CO2 saturation, is about 50% all saturated to the surface. Of course, the various kind of rocks have different permeabilities, so there is different speed in which the plume propagates upward. And as time passes by, then you get 70% CO2 saturation in the roof of the fold, 50%, and then about 30% almost all the way to the slip plane. So this is a fairly efficient way to fill in just the fold so that you can try to image the fold from the seismic point of view. Now I'll show these 5 pictures in real dimensions so it's easier to see. And so you can see again, starting from 1 hour, 1 day, 2 days, 4 days, and 6 days, how the fold becomes filled in with CO2. This is going back to our geothermal systems. You have to be very careful that the impermeable cover is very efficient. Otherwise, you're going to have gases rising very quickly to the surface if there are faults that can have a little bit of a fracture permeability. Any question?
Yes, Professor, I have a question. Is the injection of CO2 constant for the whole period?
Experiment. Yes, correct.
Yeah.
It
Okay.
is. And is a small amount of CO2 because the fault is very thin. And since CO2 is very expensive to have it on the ground and to waste it in some sense here, so we were able to model an amount of CO2 that we can provide in 6 days with about 3 trucks of CO2,
Okay.
of compressed CO2.
Thank you.
Is there any other question? So I would like now to go again and show you some of the environmental impact. I'm using again the case of Amiata, which I know the best, and for which I have very good data that in very few geothermal fields around the world have been recorded. What is interesting is that if you go all the populations around Amiata in the villages where the geothermal power plants are, then you find that there are many illnesses. Many of them are related to lungs and blood. Many of them are related to brain, particularly cancer. Brain cancer is extremely common at Amiata. Now, if you do a chemical analysis of the hairs of the people, then you find out that the hairs of people at Amiata have a very large amount of pollutants at concentrations that are much larger than what is the average concentration in normal people. And the reason is probably because they breathe these fine particles emissions from the geothermal power plants. Some of these pollutants, mercury, arsenic, antimony, uranium, also thallium, are from 2 to 50 times more of the normal. These anomalous concentrations of heavy metals in the hairs is also found in the urines and in the blood. Actually, in the urines and blood becomes particularly relevant the thallium. Now, you may know that while the hairs tells about pollution in the air, mainly in the air, because you breathe the pollutants or you drink the pollutants, is pollution that is long-standing. So in the hairs, you may have pollutions that has been going on for 2, 3, 4 months. But if you find heavy metals in the urine and in the blood, that means that the pollutions has been in the past couple of days, no more than that. So it means that this population, the effect of measuring anomalous values of heavy metals in the hairs and in the blood and the urines, it means that the pollution is sort of continuous. Where is this pollution coming from? Well, this is one of the recent geothermal power plants that was made, is equipped with abutment of mercury. Actually, all plants at Amiata now have special equipment to abut mercury and H2S and ammonia, while the mercury abutment is done with active carbons, so it should be actually be removed at a rate of about 80% of the mercury contents in the fluid. The H2S, the ammonium, and they actually are transformed into fine particles into the emissions. So, and this is the normal functioning of geothermal power plants, where you get all this pollution mainly by fine particles, and the fine particles are actually the one that constitute the condensation nuclei of the vapor that you see coming out of the cooling towers. Now, there are times at which the geothermal power plants don't work very well, and therefore they have to emit all geothermal gases to the atmosphere. And this is for a power plant that is at Amiata what happened in 2005. For a few days, you had a huge amount of pollutants emitted to the atmosphere, no abatement. And from the density and the color of the fluid, you can see how many of the solid materials were involved into this kind of emissions when the power plants don't work. Any question, please interrupt me anytime. Okay, so this is according to the reports by Enel. This is sort of the concentration of pollutants that are in the vapor that they extract. So 85–95% at Amiata is vapor. And in the Amiata geothermal field, there are 3 power plants. So there are about 400 tons of fluid that per hour goes into the power plants, and about say 300 tons an hour of geothermal fluid is directly emitted to the atmosphere. Now, most of this fluid is vapor, but 5 to 15% are incondensable gases, which are mainly made by CO2. There is a very large amount of CO2 emitted, and we said this morning that the amount of CO2 emitted at Amiata is more than for the same energy production of a gas-fired combined cycle power plant. You get 0.1, 0.2% of sulfuric acid. You get about twice that amount of methane. So there is a really large amount of methane, 2 tons per hour. Well, you can almost run a power plant with that amount. There's a tiny small power plant, gas-fired power plant with that amount of methane, if you would be able to separate it. Instead, it's emitted to the atmosphere, and as you know, methane has a greenhouse effect that is 20 times that of CO2. Then there is boric acid, and also a large amount of mercury, 10 to 100 grams per hour of mercury is emitted to the atmosphere. Let's compare a few of these pollutants to the emissions. This data has been published by Bravi and Bazzosi in 2015. You should have this paper as well so you can check the values. So these are percent of emissions from Amiata with respect to Italy and with respect to Europe, but with respect to the emissions of all industry in Italy and all industry in Europe. So 7.5% of the arsenic emitted from all industry in Italy, and 0.2 of all industry of Europe is emitted by the geothermal power plant at Amiata. A fair amount of the CO2 emitted by all industries, 0.3%, is emitted by the power plants at Amiata. Mercury, this is very impressive. Oh, sorry. 42%, let me do this. 42% of the mercury emitted at Amiata, compared to the mercury emission of the whole industry in Italy, 42% of the mercury is emitted at Amiata, so almost half. Now, if we consider that about the same amount of mercury is emitted by the power plants at Larderello, we can say that about 80 to 85% of the mercury emitted from all industry in Italy are the geothermal power plants at Amiata in Tuscany, at Amiata and Larderello. So 85% of the full mercury emissions, and this mercury is not actually accounted in the mercury emissions for industries. And this is why the geothermal power plant in Tuscany, they get green certificates, because they don't count the CO2 emissions and they don't count the mercury emissions into the atmosphere. So somewhat green certificates that are stolen to other less pollutant green or more green alternative energy production. Ammonia is 70% with respect to Italy and is about 45% with respect of Tuscany. So you can imagine is a huge amount of pollution. This mercury pollution is with the abutment in place, and the abutment system were in place about 10 years ago. So before, you can imagine, was probably 10 times more the mercury emissions. But you can imagine with this kind of emissions, why the population has such a high content of heavy metal pollutants in the hairs, in the blood, and in general in the body. I apologize for the Italians, but I try to read it in English. We said this, if we consider the mercury emissions also from Larderello, the geothermal energy in Italy emits 80% of the mercury of all Italian industries. I just make you some additional comparisons. For instance, people were very upset of a carbon power plant, carbon fire power plant in Brindisi, which is in southern Italy. This is a plant that produces 2,640 megawatts electric, while geothermal plants at Amiata emits only 60 megawatts, produce only 60 megawatts electric. Now they emit Brindisi 45 kilograms a year of mercury, while at Piancastagnaio only, they emit about 100 kilograms a year. Now, at Amiata, the amount of emission is about twice as this. It's also twice the amount of production of energy. So the geothermal power plants at Piancastagnaio emit 44 times the mercury emitted for the same amount of energy production that a carbon fire power plant. And this is with the abutment in place. The emission, if we consider there is a river that flows out from the Piancastagnaio geothermal field, and in this river, fishing is forbidden. This river is called Paglia, and is the river that goes down through Orvieto into the Tiber, which is the river that goes through Rome. Now, the total mercury emissions from the geothermal power plant at Piancastagnaio is sufficient to pollute the water that the whole world drinks in 10 years. So it's a really a huge amount of pollution that comes out of these geothermal power plants. Please interrupt me if you have any question. Now, these are more data. If we take the soil around the power plants and we try to extract whatever is soluble or easy soluble from that soil, so we find out that there is a milligram of mercury per liter of water that is extracted from the soil. Now, the limit for drinking water is 1 microgram of mercury per liter. So if you run a little bit of water through the soil, you get 1,000 times more pollution than what is allowed by law for drinking water. The herbs that you can eat, the wild herb species that you can eat, contain 0.1 to 0.6 milligram of mercury per kilogram of herbs. So the same amount of arsenic and about 80 milligrams of boron. So all pollutants which are not very nice for you if you eat. And people at Amiata, because they're used to, like in the countryside, I'm not sure about Pakistan, but in Italy, in the countryside, they like to go and collect and eat white herbs. There are,
yeah.
Sorry.
We are also doing this in Pakistan.
Yeah, so hello?
Yes.
Can you hear me now?
Now we can hear again, yes.
Yeah,
Okay.
now we can hear. It was interrupted.
Network quality. So if you are close to villages or so, try to use binary power plant with no emissions, unless your fluids, your geothermal fluids, are very good. And the reason is that, particularly in the spring and the summer,
Yes.
when there are there are high temperatures. Now, particularly at night, the pores
Yes.
of the leaves open up at night. And so all the water and the droplets of water and whatever is in the air is sucked into the leaves. And this is why you get so much contamination. Now, mud that has been abandoned around the power plants, they can get up to 50 milligrams per kilograms of arsenic and mercury. If you eat it, you die. That simply means that. Or 2,000 milligrams per kilogram, which means 2 grams per kilograms of boron. So this is actually measured by the University of Siena, the mercury in the soil close to the geothermal power plants. The one in here, this is geothermal field of Piancastagnaio. The town of Piancastagnaio is here to the lower left corners. The power plants are these in blue. There are 4 power plants, PC2, PC4, PC5, and Bella Vista, which is now closed, not open anymore. And you can see that in the soil you find 2 milligrams per kilogram downwind of the power plants. See here you get all the red spots and the yellow spots. Most of the wind is from the south towards the north. So south wind is about north of the power plants. You have a red dot here, which is north of the old power plant called Bella Vista. While upwind, you have a much better situation, upwind of the power plants. You have any questions about the pollutions around power plants?
So my question is that what you are saying at the end is that this is the minimum pollution that you can have with the state-of-the-art technology if you have the flash plant.
If you have a flash plant and you are at Amiata,
okay,
where you have the largest mercury mine, among the largest mercury mines in the world, of course the fluids are so charged with mercury and other pollutants that this is what you expect. And this is why many of the power plants that are developed in the US, they are in the desert where no people live.
Mm-hmm.
Now the Tuscan region is trying to evolve to binary. They're trying to force Enel to evolve to binary power plants, but Enel doesn't like that because of the very high content of non-condensable gases. Also, people don't like that because they're afraid of induced seismicity. One other stuff, although in the long term is not a lot, but every time you open up a new geothermal well, you need to drive the fluids directly into the atmosphere for about 15 days. So for 15 days, you have very high pollution all around with no control. And this is another problem that is related to geothermal energy. To put a well to production, you need to drive all these fluids into the atmosphere for a relatively large amount of time. So, historic problems of geothermal energy at Amiata is pollution of air and soil, decrease in the water level and pollution of the aquifer. We talked about this in the past days. Seismicity, we'll see a little bit of that, and also subsidence. Subsidence at Larderello has been over 2 meters in the past 50 years, probably even more. At Amiata, perhaps 1 meter. So we have seen the map with the geology of Amiata. The geothermal fields are to the southeast and the southwest. Main villages here is Santa Fiora and Bagnore, right into the geothermal field. Piancastagnaio and Abbadia here, right again to the geothermal field. The winds are south, mainly winds are south to north, so all the fumes from this geothermal field go northward towards 2 additional villages which are located in this east of Amiata, and what are they called? Castel del Piano and Arcidosso. Castel del Piano is out here, Arcidosso is out here. And the same, you have your power plants and your fume goes here straight into Abbadia. This is the cross section that we have drawn through Amiata, and you can see that the power plants are where you get this cupola of anhydride below the impermeable covers. And this is where you have your CO2 caps that perhaps could also be used to drain the heat out of the geothermal system. Problem with water, we discussed this a few days ago. This is the aquifer before exploitation. This is the aquifer after exploitation with the creation of a big minimum in the water table where gases can come up straight into the freshwater aquifer. This is the hydraulic head before exploitation in the geothermal system and how the recharge goes from the Amiata volcano into the geothermal system. Of course, I have drawn this arrow, but these arrows are actually flected downward. So from this area, the water goes down to about 5 kilometers and then rises up into the geothermal fields. This, how you say, this low area in the volcanic aquifer has been measured also by Manzella in 2003. She is a researcher at Pisa, and you can perfectly see that is about 100, 200 meters of water depression inside the volcano. Now, this is very interesting. In 2007, still Manzella, using magnetotelluric, has created this cross-section of Amiata in which you find the vertical magnetotelluric logs. In magnetotellurics, you measure the resistivity of rock, and red means very low resistivity, green means intermediate resistivity, and blue to purple means very high resistivity. So in these logs and in the interpolation that is behind the logs, you can see that everything that you see that is blue is dry rock. There is no aquifer. Now the aquifer is light blue. Wherever there is an aquifer, you have a light blue color. But then you have areas in which you have pierced aquifer. Like here, you see, you have light blue on top, then you have a dry area, and then a light blue again. So you have a pierced aquifer. Perhaps there are a little bit more impermeable rocks that allow a little bit the existence of pierced aquifers. But then you really need to go well down into Mount Amiata to actually find the aquifer. Now, what is interesting is that where you have that minimum, actually you have all dry rocks all the way until you find geothermal fluids, very high conductive fluids. To the right here, because of faulting, you have very high conductive fluids right below the freshwater aquifer. So you have these fluids which are right in contact with your surface water aquifer. And this is how you get pollution. Actually, she was able to measure the effect of pollution into the aquifer. Just to show this is a chimney of one of the mercury mines. In the old days was just used to bring air or actually get air out of the mine, so you could have a change in air in the mine. But now there are times in which there is a large flow of CO2, H2S, and also geothermal droplets out of this well. So the geothermal fluids are very close to the surface. This well here is only a few tenths of a meter deep into the ground. Another very interesting slide I can show you. This blue line are the oscillation of the flow rate out of a spring at Amiata. The spring is called Galleria Nuova. And you can see that from January year 1990, the flow rate was between 550 to 600 liters per second, with a little bit of oscillations that sometimes reflect the oscillation of winter rainfall and summer droughts. But then suddenly, around January 2010, the flow rate went to 550 liters per second to about 700 liters per second. So the flow rate increased by at least 50%. And this is when they closed down one of the geothermal fields. So by closing down one of the geothermal fields, they allow the flow rate of the springs to increase substantially. Remember that this aqueduct, which is mainly based on the water from the springs, bring the water to the provinces of Siena, but mainly, sorry, Siena, I'm wrong, Viterbo and Grosseto. And it brings water, particularly in the summer, to the whole coast of Tuscany, of southern Tuscany. Another effect, this is the level of a piezometer, and you can see the blue line. You can see the level of the water within the volcano is increasing until they open in 2014. They've opened a new geothermal power plants at Bagnere. And from that point on, you can see the water level is dropping down. We have seen this, well, I don't want to bother you with this. We have seen all this in the past days. Again, you can see how the temperature of the aquifer increases if the level of the water goes down. You've seen this. Let's look at the seismicity. So this is our data from the environmental impact assessment produced by Enel for the geothermal field of Piancastagnaio. So this is sort of the seismicity before geothermal energy was put in place. Not very much seismicity, very little actually within the geothermal field, and the geothermal field is given by the black line. This is the seismicity recorded by Enel within the geothermal field. And you can see that the seismicity is a very high number of earthquakes that are recorded right within the geothermal field. Now, perhaps only 10% of these earthquakes are actually felt by the population, but some of these were so strong that actually produced very large damage. Subsidence. Now, subsidence is mainly related to the decreasing pressure of the fluids within the geothermal system as you extract the fluid. This is the subsident map of the geothermal field at Piancastagnaio as measured by Enel. Now here you have about 8 centimeters up, and down here you have about the same amount downward. So the subsidence is probably the sum of these two values up and down, so about 10-20 centimeters of subsidence in 20 years, about a centimeter per year. So the ground goes down about a centimeter per year. Now, of course, this is on a very large area, so perhaps your buildings are not very affected by this, but landslides could be affected very much, but more than all, rivers. This is how subsidence is calculated, and if you extrapolate some of the larger subsiding data, like the one here, you are calculating about 1 meter over 50 years of subsidence. This is what I like you to show. There are two bridges. Let me go back for a second. There are two bridges along the Cassia. The road here is the Cassia. The Cassia is has been one of the major roads in Italy since the Roman times. And before the highway A1 was built, which actually passes about 20 kilometers west of here, this was the main road that connected northern Italy to southern Italy and to Rome. So this is the bridges here were very important. This bridge here was actually relatively recently done, about 40 years ago. This is a much older bridge that was done around the 20th. So about 10 years ago, there was a lot of erosion going on, and so the foundation of the bridges were put to the air, were excavated to the air, and you can see that this bridge here just dropped down about 20-30 centimeters. And also this bridge here the erosion went down about 2 meters. Both bridges were closed down. Now the bridge on the top, they put some new concrete on top, iron concrete, so that we're able to reuse it. But this bridge here in November last year just finally collapsed. Why is this? Very simple. This is the profile of Amiata, of course, is a cartoon before geothermal exploitation. The orange line is because of subsidence, then you create sort of a lake kind area here where you get a lot of sedimentation, but at the same time, where the bridges are that are at the edge of the subsidence zone, you start having erosion here because the river is attempting to recover its equilibrium profile. So you get Again, you get depressurization of the geothermal field, you get subsidence of the ground. Wherever the subsidence is, you get sedimentation. Wherever you are at the margin of subsidence, the rivers will start to erode. So in 50 years of exploitation, you have collapsed two major bridges in the highway system of the area. This is another thing you have to consider. So, but among with that, health is perhaps the most important negative aspect of geothermal energy exploitation at Amiata. Do you have any question?
No, Professor.
So I would like to spend possibly this last hour or this last half an hour with you discussing with you what you have learned or perhaps you have learned during this course. And I think this discussion could be very helpful for then approaching the exam. At this time would be very convenient if you would like to start a discussion, and then I will bring up the material that perhaps is useful in the discussion. You are grown-up scientists. If you have learned something by listening to me, you should be able to ask some questions if you have any.
So here it's Angela. Just thinking about what you said about the green certificate that the two plant of Larderello and Piancastagnaio or let's say Amiata were able to get. Do you think at this point, I don't know, my doubt really is what are we looking for? What are you measuring when we are providing this certificate? I'm asking this because I think something similar also happened in Germany when they decided to shut down some power plant running with natural gas while opening new plants running with coal. That I think can be something similar to the example that you were making, comparing coal with the geothermal impact. So what would you suggest for really comparing the environmental impact of this plant?
Credo si sia disconnesso.
I think Professor is disconnected now.
Yes.
Yes.
Yeah.
Okay, I'm back again up. Sorry for this.
Hello.
Can any of you hear me?
Yes.
Yes.
Okay.
Yes.
I apologize. I'm not sure
Yes.
if I went off or something else went off. Okay, so please, can you put your question again?
So my question was if, let's say, there is a different way that you can suggest for evaluating the certification, and at least for evaluating the environmental impact of power plant. Because for me it was really something new, understanding that there is this point about mercury or other heavy metal that is not considered at all inside the certification of these plants, as it is supposed that they are not emitting anything but steam.
Well, this is what was done in the past. You know, in the past, people cared very little about these problems. When environmental impact assessment became mandatory, and that is in year 1998. So for the geothermal power plant, it became mandatory in 1998. And so they started to do some improvements to the power plants, but they were always trying to show that there were not very pollution, there was no emission of CO2. And of course, it was a big business, because if you can get green certificates, then is a huge amount of money that you get for a very old technology, very cheap technology. So I can see why this has happened, and I can see also why, in many cases, even researchers have tried to dismiss that the pollution was not very much, but things at the same time come out. The papers by Basosi and Bravi show very well how difficult and how dangerous it is and how pollutant it are these power plants. Actually, there is also a study done recently by the University of Florence measuring the fine particles emitted by the power plants. And they see that the fine particles emitted by the power plants have concentrations in air, particularly for the heavy metal, that are much larger than the one you find in Florence, which the Valley of Florence is probably the most polluted valley in Italy. I mean, in the air. So there is a greater concern about this, and they've changed a little bit of laws, but there is a major problem. And the major problem is this: Tuscany, as opposed to other regions, have concentrated on geothermal energy for producing their share of green energy. They didn't want wind power plants because they said it's too bad for the landscape. They didn't want solar panels because they said it's too bad for the landscape. So they had these geothermal power plants, and they actually produce now about 30% of the electric energy used in Tuscany is produced through the geothermal power plant. But at the same time, they produce a lot of pollution. Now, they realize that they produce a lot of pollution, but they cannot shut the power plants down, because otherwise they produce zero alternative energy. And so they're sort of faking some of the data. They're using tricks of various kind to keep this power plant running, but they should not be running and they certainly should not get green certificates. I mean, a lot of the money of the green certificates is then given by Enel to the local communities, to the community, the local governments, and to the Tuscan government. So there is also a money feedback that is very relevant. Now, for a village that perhaps has only 2,000 people, they perhaps get €1 million a year. And that is a lot of money for a 2,000 people village. So I can see that even though from the scientific point of view or from the technical point of view, is not very convenient to use geothermal energy, very pollutant. They should not receive green certificates, but the local people receive some money. And even though many of them die by cancer, I mean, the communities get a little bit of money to remake the streets, to do well, whatever is more or less useful for the community. But more than all, Tuscany cannot shut down geothermal energy, otherwise the fraction of alternative energy that Tuscany has to produce goes to zero right away. Any other question? Try to ask questions also on the lessons before, because it's a good time. You are sort of fresh of all this material, and perhaps you would like to have some answers or some doubts that remain in your head.
Hello, Professor.
Yes.
First, I am very thankful to you for sharing your knowledge with us. Second, with this course, what I have learned is before this I did not know much about the geothermal energy, but now I know the geothermal energy sources, especially in Italy, and how to extract them, their formation. My question is about how to save the freshwater aquifer, because freshwater is a very important resources for human life, and how we replace this water to the sewage water or wastewater. But normally the geothermal sites are very far away from the towns and city centers. Second is the emissions and pollutions. Third is the utilization. Mean how to maximize if there is a power plant, how we can increase its production as electricity and combine heat and power. We can also use the hot water supply in the district.
So in California, they bring the sewage system of villages between about 50 kilometers away. Yes. So this is at the geysers. Before, in the year 80s, the geysers were almost going to produce zero electric power because they drain out all the water of the system. Yes. And then they started to bring the sewage system water, and from 50 kilometers away, and so they were able to replenish the geothermal system and were able to produce a lot more power. However, in the long term, I think from now on, what we have to look at is really this new kind of technologies, like closed circuits, like the closed loop circles, like the EVOR technology, or the project in Japan in which they have closed circles, closed loop, but only on one well, on single wells. But that works only if you have very high temperatures. Also getting more efficient and cheaper plants, and the thermoelectric effect could be used, and it could be a very efficient way to produce electric energy. You don't need turbines, so you don't need moving parts. In the very long run, if we would use graphene, could be the ultimate way, but graphene is very expensive, so I see it very far away in the future. Geothermal power plants, by the way, are very interesting for armies, because particularly in the desert or very far away from power grids, the army need to set up stations and have electricity produced, and if they can get it right off the ground, it's very good for them. So some of these projects are actually financed by the US Navy and US Army. Some of these kind of new technologies. One of these new technology was in the Navy field, in the Navy geothermal field that is in Coso, in California. So even if you or I don't like the armies, some of the good stuff can come from them as well. Geothermal energy is probably going to be a very good energy to try to develop on Mars once we get there. There are very large volcanoes. There are certainly going to be very hot temperature at not very much depth. So that is a good energy that probably we can use on Mars. The atmosphere of Mars is mainly made of CO2, so perhaps you can pump just straight the CO2 from the atmosphere of Mars down into the geothermal system and flush it back up again into the atmosphere. The atmosphere of Mars is not very nice. That for sure in the first place.
Yeah, one more question, Professor.
Yes.
In the morning session, you show us your paper in which there are 4 wells, green and one is the red. Could you please explain us why the green wells have more depth and the red well has a very small depth?
Okay, this is very interesting. Now, because I wanted to use CO2, and the density of supercritical CO2 is about half, 1/3 that of water at that depth. So still the supercritical CO2 plume is very buoyant with respect to water. So if you want to collect your CO2 plume, you need to collect it well above the place where you are injecting it. So you're injecting it 1 kilometer deeper, about 500 meters away. So the distance between your production well and your injection well is about 500 meters, and you're injecting 1 kilometer, so 1,000 meters down. So this plume, as it develops, it can slowly move sideward towards the production well. But if you want to produce that CO2, you need to be at a much higher elevation than the place where you are injecting it.
Okay. Thank you.
Thank you to you, Id.
Thank you.
Chiara, c'è qualche domanda?
No, al momento no. No, I have no question at the moment. It's very interesting and impressive. Know that the use of geothermal energy can have a very big environmental impacts and important negative effects, because usually people consider geothermal energy a total green system of energy production.
Don't take it so negatively. You as an engineer or engineers in general, are there to try to solve these problems from the technical point of view. So there are ways to solve these problems, and there are different approaches, and you can use abatement of pollutants, although this is not, for the case of Amiata, is not good enough. Or you can use different drilling technology, like the shale gas technology, but in particular, if you are going to use low enthalpy geothermal energy, then that is usually totally green, because you're much closer to the surface, you're using hot water from aquifers that are not very polluted, like the one at Amiata, where you have very polluted geothermal fluid. So don't take it very negatively. Take it in a very positive way. If there is a problem, once we know the problem, you are able to think about how to solve the problem. If you don't know the problem, that you're never going to solve it. However, superficial geothermal energy, low enthalpy geothermal energy, the one you can use to warm up the houses in winter or cool down the house in the summer, is very cheap, very inexpensive, and very clean. We hadn't had time to go through this, but because that has less problems, I'm sure it's easier to solve and easier to get to, to use.
Okay.
Ettore.
Yes, I'm here.
So some questions from you.
Yes, I'm agree with you that technology is not good or bad, but is the use of the technology to make it bad. So my question is, as the geothermic fluid of Amiata more heavy metals than other geothermic fluid uses around the world?
I think yes. At Amiata, the fluids are probably the worst you can get.
Okay.
Now, for instance, in Iceland, because it's the whole island is a volcano, and because the whole geothermal systems in Iceland are related to volcanoes, you get nasty geothermal fluids, but mainly is H2S that is the problem. And so they have a number of projects to try to avoid H2S emissions. Some of these emissions really go all the way to the capital city Reykjavik, and have been seen that they produce some health problems there as well, but certainly not as big as Amiata. Just to give you another example from Amiata, the high school of Amiata has about 15 professors, and at least 4 of them have died by cancer, brain tumor. So it's really a fairly large amount.
Is because somehow the Iceland geothermal system is newest than the Amiata?
No, I think it's because the magma is different. The magma in Iceland that feeds the volcano is more basaltic, more primitive, has less gases. The magma instead at Amiata is anatectic. It comes from fusion of the lower crustal rocks, and those rocks are already full of accumulated pollutants. You know that in geology, you know that the more primitive magma are the basalts, and then the magma in time crystallizes, and so the liquid phase of magma evolves towards more acidic rock, which there becomes more and more enriched in the more volatile components like the heavy metals that we are seeing at Amiata. So Amiata is very particular because it has a lot of pollutants that are accumulated in the more silicic fluids of magma.